everybody, Rockpile Tutors here, doing a little shift change over to chemistry for a bit. I worked on these problems with a student and thought it would be valuable for some other of you because I guess the test is coming up, so hopefully you get a chance to watch this and learn it. We are going to look at energy flow in water as we go between solid water or ice, liquid water, and gaseous water or steam. And then what we're going to do here is we're going to look at the different things that we can do. So let's look at the states of water. Water has a gaseous state, also called steam, and that is when the temperature of the water is greater than 100 degrees C. Right? The definitional points is boiling at 100, freezing at 0. Liquid, also known sometimes as water, is when the temperature is greater than 0 degrees C, freezing, but less than 100 degrees C, which is boiling. And finally, the solid form of water, which is ice, when the temperature is less than 0 degrees C. So there's a few things that we want to do. We want to look at the movement, the energy. So this is always going to be energy, and the energy as I move between temperatures in the same state. So let's say for ice, let's say I'm at minus 20 degrees C and I want to go to minus 5 degrees C. And I have a block of ice that weighs 100 grams. All right. That energy is going to act on each gram, and each degree it's raising by using the heat capacity of solid water. So the calculation will be, and this is warming, so it'll be a positive energy. You put energy into the system, and the energy of warming as a solid is 2.1 joules per gram degree C. And this is interesting because you can use the constant and look at the units and know what I have to multiply. So in order for that 2.1 joules, that is for 1 degree Celsius increase in 1 gram of water. But we have 100 grams. So the first thing I'm going to do is I will cancel out the grams by putting in 100, which is the weight of my sample, or the mass of my sample. And then the degrees C, how many degrees C am I moving in the same state? I'm moving 15 degrees C. That energy that it costs me to make 100 grams of liquid water go from minus 20 degrees C to minus 5 degrees C is 2.1 times 100 times 15 is 3,150 joules. And the way I'll show that is like this. This is what a warming, which would be positive energy, or if it were cooling, it would be negative, but it will all be in the same phase, or doesn't change from solid to liquid. Now we can continue doing that, and I could figure out that warming curve to go up until 0 degrees C. Right? Once I'm at 0 degrees C, it matters whether I am a solid or a liquid. In this case, right as we add enough energy to get that block of ice at 0 degrees C, it will still be in the solid phase. The next step takes energy to just convert it to the liquid phase, which does not change the temp. This is critical because we're using a different format. So picture 100 grams of water at 0 degrees this, I have 100 grams of water, 100 grams of ice, which is solid water, at 0 degrees. To get it to a liquid, I need to put in energy, which is called fusion. So without changing temperature, I'm going to put in some energy. Now, you normally think of fusion as things coming together as a solid, but it works both ways. So fusion is the same energy to go from liquid to ice as it is to go from ice to liquid, just positive or negative. In this case, we're adding heat to it, so it's going to be positive energy, and the energy of fusion is going to be 334 joules per gram. You'll notice there's no temperature, there's no degrees C in this formula because the temperature doesn't change at the phase change. It just adds energy and changes to liquid water. So it's going to be times my 100 grams. Grams will cancel, and I will get, because I can do this, 33,400 joules just to change all of that ice into liquid water. So if I were to do both of these, then I would have some energy that it took to get it up to temperature, and then it takes the energy of fusion, and you'll notice that this energy is much more significant, right? So raising 15 degrees is 3,000 joules, but converting that same amount from solid to liquid is 33,000 joules. So it's a significant, most of the energy goes in the actual phase change. So now let's talk about liquid. When I now have water, I have 1 gram, well, let's make that more. Let's make that my 150 grams of water. It's at 0 degrees, but it's liquid. So I am going to warm it as a liquid up to 22 degrees, which is typically known as room temperature. So my equation will be the energy will be the heat capacity of liquid water. So 4.18 joules per gram degrees C, again, needs 2 additional pieces of information. It needs the weight of the water, not equals, times the weight of the water, which is 150 grams, times the number of degrees that I'm going up, or 22. In this case, that energy is 4.18 times 150 times 22, or 13,794 joules. So that, just that bit would take me 13,794. And then finally, the phase change, not finally, but the next one will be at 100 degrees, where again, I'm making a phase change from liquid to gas. And this, once again, will not change the temperature. It will just take energy, and this energy is called vaporization, because I am taking a liquid and turning it into a vapor. So, and you'll notice this is also the largest number on the page. So the energy to vaporize is 2,260 joules per gram. Once again, no temperature change because this happens at the boiling point, times 150 grams. is 339,000 joules. 339,000 joules. So you see, each of these energy changes becomes more and more expensive in terms of energy. So now let's take a look at some problems where we are going to combine these things and have to follow the energy. And I've got my problem. How much energy must be absorbed by a 150 gram sample of ice? So there's my weight, there's my phase, and my initial temperature. So energy must be absorbed, meaning I'm adding energy. So I will draw my graph, my energy line and my temperature line. So where am I starting? I am starting with a block of ice, and that is 150 grams. That's a terrible color. 150 grams at 0 degrees and as ice. So what has to happen here? At 0 degrees, we first need to make a phase change from solid to liquid. So that is going to be fusion. And my energy of fusion is solid water, 334 joules per gram, times the number of grams I have, 150, is 50,100 joules. So after the first step, I'm going to go 50.1 kilojoules. That's my energy level after I have created liquid from all of the ice. All I did was phase change. There was no temperature. This is now 150 grams of water at 0 degrees, but it is now liquid. And now what do I want to do? Now I want to warm that to 25 degrees. So I have my 25 degrees C here, and I'm going to go from this energy level, and I'm going to warm or heat, and using the heat capacity. So I'm warming as liquid, and that's important to choose the right constant. So my energy there is heat capacity of liquid water, 4.18 joules per gram degrees C, times how many grams, 150, times how many degrees, 0 to 25 is 25. That amount just for the green there is 150 times 25 is 15,675 joules, because all of my canceled out, because this is grams, this is degrees C, and just this amount what are we doing here? Okay, so that amount is 15,675, but the level that I've put in from the beginning is that number plus 50,100. So the total to do this entire activity is 65,775 joules, because it has two phases. First, I do the phase change to liquid, and then I warm the liquid. So this is going to be the answer, 65,775 joules. Tried to write grams, joules. All right, does that make sense? I sure hope so. Let's give another one a shot. So problem 2. Now we're going to figure out what the problem asks. We're going to add a set amount of energy to 450 grams of liquid. So that sets our starting point at 20 degrees C. I'm going to draw my axes, my energy, my temp. I have 0 degrees, and I have 100 degrees, and 100 degrees is where it goes from liquid to gas. And where am I starting? I'm starting at 20 degrees. So the question asks, how much of the water would be boiled away? Which suggests that we're first going to get up to 100 and then talk about the phase change. So my first step, let's set my 0. I've got 450 grams of liquid at 20 degrees C, and I need to get up to 100 degrees C, staying liquid, and I want to figure out how much energy that costs to do that. So because it's liquid water, I'm going to use the heat capacity of liquid water. So the energy is going to be 4.18 joules per gram degrees C times the grams, which is 450 grams, times the degrees C from 20 to 100 is 80. That is going to cost me, what's it going to cost me? 4.18 times 450 times 80. So it's 150,480 joules to get it up to here. So 150, 480. And now I'm going to start the fusion process, or sorry, the vaporization process. From here, there's going to be vaporization until I have spent 325,000 joules, because that's all I'm putting in. Now let's figure out how much that is. So 325,000, subtract the 150,480 to get me up to the boiling point, and I've got, so this distance here, the energy that I'm going to spend is 174,520 joules. So let's think about, from our constants up here, what am I going to be doing? I'm going to be vaporizing, which will cost me 2,260 joules for every gram times the weight of liquid that becomes gas, but I already know that that's going to equal 174,520. So in order to find out how much will make it through that transition, I'm going to divide by the number of joules it takes to make 1 gram. So this will tell me how many grams I get to bump from liquid to gas. So 174,520 divided by 2260, and the answer is 77.2 grams will be boiled. All right, so what mass of the water would be boiled away? 77.2 grams. Now, I have energy and temperature in degrees C. At 0, I've got solid and liquid. At 100, I've got liquid and gas. This is the way I like to set it up so I can start my movement. So what is my initial state? I've got 340 grams at 25 degrees C. And obviously it is liquid. All right. I'm going to put it in a freezer, and eventually it will get down to negative 12 degrees C. And it wants to know how much energy must be removed which means we are adding negative energy because we're cooling it. And just as a picture, what I'm going to do is I'm going to sketch out what we do. First, we're going to cool, right? We're going to cool till we get to 0 as ice. And then, hopefully you are saying this as you're watching this, then I am going to do fusion in reverse. So I'm going to convert 340 grams from a liquid to a solid. Again, we'll take energy out, so I'm going negative into energy here. And then my last step will be to cool as a solid to negative 12 degrees C. So all of these, hopefully, so we're not going to use boiling at all, but I'll just put it here, but out of the way. So hopefully all of these will do a calculation and we'll be able to add the values. So first I've got cooling as a liquid. So energy cooling as a liquid is, that's heat capacity of liquid water. And I'm going to do this in the positive, but you need to know whether you're adding or taking away. So this will all be negative energy, but I'm going to do it in the positive and switch it. So this will be 4.18, because I'm liquid, joules per gram degrees C, number of grams, 340, and the number of degrees C, it's going to take me from 25 to 0, so I'm going 25 degrees C. This equals 35,530 joules for the cooling. Next, I have the fusion, and in reverse, so it'll be negative. And that is the heat of fusion. E sub fusion is 334 joules per grams times 340 grams equals 113,560 joules. And you'll notice, in a negative way, right, that these will add to get the current state. So if I were to add 35 and 113, that would give me 340 grams at 0 degrees already converted into a solid. And then the third section is, or the third energy expenditure is cooling solid water. So that is the energy of cooling as a solid is 2.1 joules per gram degree C times 340 grams times, how far are we going? From 0 to negative 12 degrees C. And that is 8,568 joules. So that gives me my 35,000, 113,000 to get it to solid, and then 8,000 to get it to minus 12. And if I add those together, and 85, 68, right? That whole excursion from 25 degrees to minus 12 will be 8, 5, 6, 13, 14, 7, 5, 157,658 joules. Again, we look at everything that's happening, we calculate the energy separately, and then we add them together. So let's draw. What's my initial state? So I'm going to add kilojoules to ice, and we're going to have the final temperature of the water. So I'm going to be moving with positive energy this way. So 0, and I've got solid liquid, and I'm sitting with my initial state is 150 grams solid water or ice at 0 degrees. So what's the first thing I'm going to do? I hope you will all say fusion together, because the first thing I'm going to do is I need to melt all of that ice. So the fusion energy is fusion from melting or freezing, 334 joules per gram, times, how much do I have? 150 grams. $50,100. Right? And remember, that's this energy level here. Now, I've already been told that my total is 65,000 joules, which means that I'm going to increase my temperature, because I'm all liquid water, until I get to temperature T, and the equation will be 65,000 minus 50,100, right? This is the amount I have left after melting it, times, equals, so that's the energy, and that energy equals the heat capacity of liquid water, 4.18, times the amount of water, 150 grams, times T degrees. So in this case, I'm solving for T. So what I'm going to do is I'm going to have 65,000 minus 5,100. So this ends up being T equals this, which is 14,900 divided by this. So 14,900 over 4.18 times 150, 627. Which is 23.8 degrees C. So if we have the energy, we can find the temperature, right? We could say how much water would increase, but in this case, they gave us the water and they said, when I put this total amount of energy, and you have to recognize that the first chunk of it is spent to melt the ice, and then we warm it up. And that amount is going to be 23.8 degrees C. So this one, a little confusing because they throw some scientific notation at you, but hopefully you remember that we can just use this as we've been with the other ones, and you can convert that to 400 grams. So let's set up our initial situation. We're going to be removing energy, so we're going to be going negative. So I'll draw my axis like this. My energy in joules, my temp in degrees C, and what's my initial state? All right, sorry, 0 degrees C. I have to go from solid to liquid. 100 degrees C, I need to go from liquid to gas if I'm in that area. But for today, for this problem, I have 400 grams at 60 degrees C. And now what's going to happen? Will the sample of water completely freeze with 250 kilojoules? So if I put 250,000, if I take 250,000 joules away, so that would be negative energy, I'm pretty sure right? My first step will be cooling it down to 0 as a liquid. And then I'm going to need to do the heat of fusion to get somewhere here, and this total is either less negative or more negative than 250,000, and that will determine whether everything got frozen. So first we are going to be cooling a liquid. So energy is going to be heat capacity of liquid water, 4.18 times 400 grams. I'm leaving my units out. Hopefully you've been following. Times how many degrees? 60 degrees. So my first step to get everything to liquid water at 0 degrees is 100,320 joules. So that's this point here, 100,320, and because we understand the problem, we're going to put that as a negative. Now, let's figure out the energy of fusion. So effusion is 334 joules per gram times 400 grams. That equals 133,600. So if this amount is 100,320, and this amount, this amount is 100,320, this amount is 133,600, I think you can see that the total amount of energy removed is 233,920 joules, which is less than 250,000. So yes, water will completely freeze. Right? And hopefully you can explain using this. Question 6. Let's figure out what we have. We have an ice cube tray with 235 grams sitting at -7, and I'm going to warm up. So my energy is going to be a positive here. So I'll set myself up here, start at -7. I've got 0, and 0 is my solid to liquid transition, and 100 is my liquid to gas transition, and this is energy. So what does my sample look like? My sample says 235 grams and it's solid at -7 degrees C. All right, and then it's going to go up to room temperature, which is 22 degrees C, positive 22 degrees C. So let's quickly sketch out what's going to happen. I'm going to have warming to 0. Then I'm going to have fusion to liquid. And then I'm going to have warming of liquid to 22 degrees, which will be 3 chunks of energy culminating in the total amount of energy that I put into the system, or I allowed to be put into the system, to get it from where it is to where it ends up. We can attack each 3 separately. So first I'm going to be warming solid ice. So the heat capacity of solid water, 2.1 joules per gram degree C times 235 times, I'm only moving 7 degrees here. So that initial energy is 3,454.5 joules. Next, my fusion, which is typically the big deal here. So my heat of fusion is going to be 334 grams, 334 joules per gram times only the weight is all I care about because it's phase shift. 235 grams equals 78,490.